Hey guys, so this video lesson, we're going to talk about molar volume and solution stoichiometry. This one's going to be kind of a quick one. I know that's so disappointing. So let's just start with Avogadro's law. And Avogadro's law is just telling you that the volume of any gas at a constant temperature, it's important that the temperature is staying constant, and that the pressure is staying constant, is going to be directly proportional to the number of the moles of the gas. So it's the same volume is directly proportional to the number of moles of the gas. And that's the equation written here. Sometimes you see it written just, volume 1 over N1 equals volume 2 over N2. And then, of course, you could also say then volume 1 times N2 would be equal to volume 2 times N1. Either one is acceptable. And really how this comes down to play is just like the example here right below. Looking at this example, how many liters, right, so we're trying to find out how many liters of water vapor can be obtained from the complete combustion of 24 liters of methane gas. And it's telling you to assume that the temperature and the pressure are such that all water form will be in the gas phase. This is a very elaborate way to say temperature and pressure are constant. Okay. All right, so the first thing you would need to do for this type of problem is, of course, write out the equation here for the combustion of methane. Hopefully you recall now that CH4, this is methane, and of course combustion means you're adding oxygen gas, methane being a hydrocarbon, that is carbon plus hydrogen is producing carbon dioxide and water. And then once you've written that equation out, so you're going to write the equation, and then you need to balance the equation, of course. And that's what I went ahead and did for you here. So you have 2 moles of water, this 1 mole of carbon dioxide, 2 moles of oxygen, and then 1 mole of methane. So going back to the problem here, we looked at, we had 24 liters of methane, and we're trying to figure out liters of water vapor. So we're trying to go from this 24 liters of methane to liters of water.
Attention Eagles. Tonight at 6 p.m. is a girl.
All right, back to the problem here. So again, we're just taking this 24 liters of methane. We're trying to find out the liters of water. And look how simple this is. We've got 24 liters of methane. This right here, this 2 liters of water over 1 liter of methane. This is the same thing. You could write it like 2 liters of water divided by 1 liter of methane. What is that? That is a mole ratio from your balanced equation, right? Right, so this 2 here, this is because of the 2 moles of methane, of water, excuse me, and this 1 here is because of the 1 mole of the methane. And so that's all you're doing, literally. Multiply across the top, 24 times 2, and you get 48 liters of water, because essentially divide by the bottom. That is it. That is all molar volume is that understanding that the mole ratios, right, mole ratios are equal to volume ratios. Right, that is the big key right there, that they're directly proportional in the balanced equations. One other last thing about molar volume. Okay, last thing about molar volume, just to remind you yet again, is you have what's called 1 mole for every 22.4 liters at STP. Remember, STP means standard temperature and pressure, which those conditions are 1 atmosphere 0 degrees Celsius, or the same thing as 273 Kelvin. And so just remember that, and you can write those off as any proportion. So if you're converting from moles to volume, you know that this is your conversion factor, 1 mole for every 22.4 liters. And that's it. If we wanted to convert this 48 liters in, we could say this 48 liters, let's say it was at STP, then we could say there's 1 mole for every 22.4 liters, and get the exact figure here, 2.14 moles at STP. That's it. That's your lesson on molar volume and solution stoichiometry.